Well, welcome back, everyone. I think we can officially start. We have a good balance. We definitely have a representatives here in person and representatives on Zoom. I appreciate you all making it today. These are the harder weeks I think it is to get through, but we're definitely going to make it. Right now, we're currently done with chapter 19, and we're about to break into chapter 20. I don't expect this one to be finished today. Probably we're going to finish it off when we come back on this week right here, which means we may start the chi-squared methods as well in the very next section. But then on Thursday of that week, we may have an impromptu review. We'll give some reminders about that before we get into that next week. And we'll also, like I mentioned before, be working over the weekend, starting on Friday, doing the grading and putting in information here. Majorly starting with the formula sheet that's going to be attached to exam 3, since that will inform quite a bit on how you study. So that's where we're at so far. Excuse me. Any questions at the moment, folks, then, to start us out today? Okay, well, let's take a look at what is going on in chapter 20. We mentioned before, chapter 19 parallels chapter 17 very strongly. And same thing with chapter 20. Chapter 20 is paralleling chapter 18 quite a bit. So let's take a quick look into how that chapter started, just to orient ourselves. In chapter 18, we're comparing two different means. They are coming from independent populations. Same is true with chapter 20. Only difference now is, instead of having, let's say, distributed with, let me restart my thought. Instead of the populations both dealing with quantitative data, we'll be back to the situation with categorical data. So still two independent populations, but now we're looking into the difference between P1 and P2, much like how this was the difference between mu1 minus mu2. In fact, it starts off basically the same way. We need to cite the central limit theorem so that we can redevelop the central limit theorem for a difference in p hat 1 minus p hat 2 instead of the x bar 1 minus x bar 2. So here's how it starts off in earnest. Oh, I think I already pulled it up. Chapter 20 cites the same exact theorem that we've been looking into before. The theorem is about the mean of adding and subtracting two random variables. We're mostly interested in the subtraction of them. Variance is about the difference in the two variables. Adding or subtracting will always get an increase in the variance. And so now here's how this starts. We need independent random samples. So we need to check that part of the theorem. But that's the assumption in example 1. Example 1 says, gather two independent simple random samples. Sample sizes are indicated this way. We need that information for the central limit theorem. But the new change is, this time, we're dealing with categorical data, population proportion of successes, P1 and P2. Because of that information, the data is categorical, and there's specifically two outcomes for them. And then this is just the restatement of the central limit theorem twice. We'll say here, by the central limit theorem for proportions. This is the theorem that we stated in chapter 19 that got us going, analyzing one single proportion. We can now say p hat 1, excuse me, is distributed normally. The center of this distribution is going to be the first parameter, P1. So we draw P1 here. Standard deviation is then going to be P1 times 1 minus P1 divided by N1. So that's that central limit theorem we were working on last chapter. N1 is the sample size from the first population. P1 is the parameter, the true population proportion of successes from the first population. So P1, and then P hat 1 is just the sample's proportion of successes. So once we do that, unknowingly we have to do it again, but only change here is now we're talking about the second sample size, the sample from the second population. So we're referring to P2 here. That parameter P2 is estimated by p hat 2. Let me keep the color coding the same though. Same limit theorem, central limit theorem says this one is also distributed normally. Parameter values P2 for the center. And then for the spread of this distribution, we put in P2 times 1 minus P2 divide by N2, since this is the sample's second sample coming from over here. So now we have both of the distributions down. We're going to use these elements, parts 1 and 2 of the above theorem, to get the approximate sampling distribution of P hat 1 minus P hat 2. So part C is the new thing that we really wanted. And just like we did before, it's a good idea to do this in stages. Let's take a look at what we did in chapter 18 first. But any questions at the moment with where we're at? Okay, so just to get some motivation of what we've already done in the past, excuse me, I think the spring weather's starting to affect my lungs. Chapter 18 says, first thing we want to get is the mean. That would be mu1 minus mu2. And that's from this part right here. We just take the parameters, subtract them. That's the new mean. But this gives us information on variance. So now what we need to do is square this to get variance, square that again to get variance. Then the theorem above says the variance will add together. So that's the variance being added. Take the square root, and then we have the standard deviation to drop in. So we collect both results back into the central limit theorem. And that's exactly what we're about to restart. But now for P hat 1 minus P hat 2, the sample proportion of successes. So let's give this a try. It's nice to see it done once because now it's kind of like a structure in our mind. We'll take the same exact approach. We're interested in the distribution of P hat 1 minus P hat 2, but working through in stages with part 1 of that theorem, we'll say P hat 1 minus P hat 2 has mean. We take the first mean, mu1, that's going to be the first part of this theorem, referred to as mu x. Then we're subtracting here, so we keep the same sign on the above right here. We go minus. Take the second mean. It says mu y, but it's just referring to the second distribution down below. So subtract and get P2. And this part is directly the same as what we did before. It's just P1 minus P2 instead of mu1 minus mu2. But then some really interesting changes do occur here. One of the reasons we do this kind of short exercise is to see what happens to the standard error. Standard error gets a little bit more complicated in this section. And we can see why once we go on to the next stage, dealing with the variance. So step 2, we'll say the variance of, let's do this singularly, and then we'll put them together. So first, the variance of P hat 1 is, if we're dealing with variance, we have to go here. In statistics, this is a standard deviation. In probability, that would have already been a variance. So in the statistics setting, we need to square that quantity. Variance is root P1, 1 minus P1, divided by N1, squared, giving us just a P1, 1 minus P1, divide by N1, written as now a standing upright fraction rather than the sideways version. We need to do it again for the second group right here. So let's say the variance of P hat 2 is same structure. We just have to be mindful of the subscripts. So go square root P2 times 1 minus P2 divided by sample size 2, pulled from the second population, square it, and now we have P2 times 1 minus P2 divide by N2. Now we are finally ready to use part 2 of the theorem here. Even though we're dealing with P hat 1 minus P hat 2, whether you're adding or subtracting two random variables, the random variables are P hat 1, P hat 2, variance always adds no matter what. So the variance of P hat 1 minus P hat 2 is going to be these two parts right here added together. Let's say this implies variance of p hat 1 minus p hat 2 is, gather these together, just add them now. Let me scroll a bit up to show, it's kind of hard at this point. Show the theorem right over here. So I'll go P1 times 1 minus P1 divide by N1 plus P2 times 1 minus P2 divide by N2. That's the variance, but the moment we take the square root of that, it's now the standard deviation. That's all we needed. The right mean, there it is. Right standard deviation, square root of all this. And then we just bring it back together for a new distribution like this one above. This is going to be our new central limit theorem for difference in p hat 1 minus p hat 2. So here's that next to last step. Let's say here, and so, forgot a letter, and so the standard deviation is square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. And starting to get kind of messy, but categorical data is messy in a lot of different ways. Formulas being messy is just another manifestation of it. We're about ready to state our main conclusion. We can say, therefore, the sampling distribution of p hat 1 minus p hat 2 is distributed. This distribution is approximate. But we'll give conditions on when it's a pretty decent approximation. So this will be distributed normally. We bring in the mean that we calculated. So this is P1 minus P2. So that's the center of the normal distribution. We bring in next the standard deviation, this entire structure. So square root of all of that. P1, 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. I think we finally got it, folks. This is now our new central limit theorem for a difference in statistics, p hat 1 minus p hat 2. The major critical thing about this is we really had to have two independent populations. But any questions at all, folks, getting to this stage? Okay, then following the, again, really strong parallelism to our methods in chapters so far, 17, 18, and 19, we know we can do all of our statistical inference the moment we have an appropriate standard error. So we're estimating P1 minus P2, which means both P1 and P2 are unknowns in this process. So we don't know anything about this information in real statistical inference, and we don't know anything about this either. Yet we've got to approximate that part right there. We call it a standard error as a standard estimate, and it looks like this. We'll say, for standard error, p hat 1 minus p hat 2, it's often abbreviated as simply SE for standard error, but that's context sensitive. You have to know you're in chapter 19. Being more descriptive takes away the need for the context. So I often call this SE of p hat 1 minus p hat 2. So that's our new standard error. Coming over here, we make the observation we can't throw that in, but P1 is approximated well by p hat 1. We're just throwing in the statistic is the idea next. P2 is well approximated by p hat 2. So we even have estimates on this, but we don't have any notion of the error in that estimate. To get that margin of error, we go over here, call this a standard error, and it becomes square root of, in place of all the p-values, or I shouldn't say p-values, that sounds like hypothesis testing. In place of all the P1s and P2s you see right there, just replace them with the appropriate approximate statistic. So back over here, it's P hat 1 minus P hat 1, divide by N1, plus P hat 2 times 1 minus P hat 2, divide by N2. And let me make a small change in the color coding. Last step was more about the estimate, so let me put the sample sizes in black. And that's our standard error. Slightly more complicated structure than we're used to, but it's nice to see that same process going in that same type of order. With the standard error in play, we're essentially ready for the large sample confidence interval method. Let's put that on the next page, just for the sake of not putting too much on one page. Any questions at the moment, folks, with the conclusion of that first example? Okay, well, before we take a look into the methods, let's just look into a little bit of review on this. When we were in chapter 18, our methods for, say, a confidence interval were x bar 1 minus x bar 2, add or subtract t star. We had to use a more complicated distribution because our central limit theorem is on 2 parameters, making it much more complicated. And then we just multiplied by the standard error, x bar 1 minus x bar 2. Looking at this standard error, notice how similar the structure kind of is really. Sigma 1 squared divided by n1, sigma 2 squared divided by n2, square rooted, gives you this as a standard error, s1 squared over n1, s2 squared over n2. Same idea, just a little bit more complicated because we have p hat times 1 minus p hat, which is just a residual part of dealing with the binomial distribution. So this was the full confidence interval method in chapter 18. And now in chapter 20, this is what we do this time. We're doing p hat 1 minus p hat 2. Because our data is categorical this time, we add or subtract a z star, but that's because, well, this is specified by just one type of parameter, p, not a second parameter like mu and sigma. We multiply it by the standard error of p hat 1 minus p hat 2. And that's the thing that we just derived right up here. So we're in good shape for our methods. Z star is exactly the same one that we used in chapter 19, so it's really fast to get that same exact critical number. And maybe one more reminder. The reason you use this confidence interval above is because you're trying to estimate between A and B, whatever those numbers are, mu1 minus mu2, the difference in population means. But this time, what we're trying to estimate is the difference in population proportions P. So whatever that interval outputs, we're going to get a different value. Maybe let's call it, alpha's a bad idea. Let's just call it a different A, less than P1 minus P2, less than B. So the estimate is trying to do the same exact thing. We just have to recall the parameter is different. We're estimating the population proportions between two different independent populations, not the population means. Well, we're about ready to specify the full method and then practice a problem. Any questions at the moment with either one of these approaches? Okay, well, here is then next, the large sample confidence interval for comparing two proportions. First thing, we have to have two simple random samples from two independent populations. This is the new part. We have to really know our populations are independent. So that's a hard thing to justify, but if we read through the problem, that should be something that should be plausible or something we might decide is implausible depending on the setting. Next thing we look into is, well, let's also mention how we analyze this. For part one, always we just briefly discuss. Now, in part two, this is where we have to be very careful. So here, carefully check. And just like in chapter 19, also show the number of successes and failures in your samples, just like we did in chapter 19. Show the actual counts so that I know that you know which values that would be. But also notice the Stark changed this time. Well, it is a large sample confidence interval, so we expect a large value for our total sample size. But the actual requirement here says number of successes and failures in the sample, not like hypothesis testing, which is expected successes. Has to be greater than 10 for the first, this is successes. The failures has to be greater than 10 for the first sample as well. That as the subscript changes, N2 p hat 2, we're talking about the second sample. 10 successes, 10 failures. So at minimum, we need a sample size at 40, but in reality, it's probably over 100 if either one of these proportions is close to a 0 or close to a 1. In fact, in the last chapter 19, we saw data that was around 150 observations, didn't even meet the conditions at that sample size. Last thing, you don't have to check or mention on your paper, but if you did, it wouldn't be harmful. Just something to be, again, always cognizant of. Our methods break down in a pretty major way if the sample is really large relative to the population, which will cause problems if you're studying something that has a rare occurrence, maybe a rare genetic disorder, something where there's actually a small population for. There's ways around this if this ever occurs. We do something more probabilistic, something using now the binomial distribution instead of essential limit theorem. But if everything falls in line, here's our confidence interval method that we mentioned, I meant to say. We take the difference in the parameters, the difference in the statistics, p hat 1 minus p hat 2, that's estimating the parameters p1 minus p2. Z-star makes another showing, which is a comfort. The standard error, well, it's complicated, but we've gone through worse. Think of, say, like the degrees of freedom in chapter 18 was a lot worse than that. Just a reminder, looks like this. Sometimes statistics just gets out of hand a little bit. That will be a provided formula on the real exam 3. So that's our full method. We're going to try it out immediately to answer this interesting question. Is cocaine deadlier than heroin? This is in a laboratory setting, not necessarily in general. But any questions at all, folks, with the methods? Okay, let's give this all a try. We'll cite the formulas above right as we need them. And here's how it goes. Let's maybe put this on the next page too. So, interesting question to start off this problem. Is cocaine deadlier than heroin? I would say heroin is because it just seems really nasty, but I'm thinking human behavior really. This is a very specific context. It says a study reported in the Journal of American Medical Association found that rats with unlimited access to cocaine had poor health, more behavioral disturbances, and died at a higher rate than did corresponding groups of rats given an unlimited access to heroin. So really bizarre study, but you've probably read about these kind of studies before, how mice or rats behave in these kind of bizarre scenarios. Really, we're trying to study human behavior, but we're doing it first through seeing what happens in laboratory animals. So they go on further to say how this experiment worked. It was an experimental design. That's nice to hear because that gives us random data. 200 rats are randomly assigned to the 2 treatment groups indicated in the table below. So that random assignment gives us 2 independent populations, and now this is considered to be random data. They tell us the death rate after 30 days. Actually, this is more of the context of what's going on. So these rats had unlimited access to cocaine for 30 days, unlimited access to heroin for 30 days, and the death rate was 90% dead rats in the cocaine group. Looks like cocaine was deadlier, and 36% of the rats are dead in the heroin group. So pretty stark statistics on that. It says, give a complete analysis of this data. We'll give a confidence interval at 99% confidence. So that's how the problem starts. Again, the question is kind of really misleading, right? The context is all about which is more deadlier to rats in a controlled setting where they have unlimited access to either drugs for 30 days. Cocaine was the harmful one, it looks like. Let's break this down a little bit further. 200 is not the sample size, really. That's just the total combined sample sizes from both independent populations. So let's start to specify this by maybe saying for the cocaine rats, sample size was, we could call this N1, N2, or maybe NC for the cocaine sample size, NH for the heroin sample size. Really totally up to you. We haven't done it this way often, so maybe let's go this route, more descriptive subscripts. NC will be 100, and H will be 100 as well for the heroin group. This is an interesting study where usually you wouldn't want your laboratory animals dying off because that would be a really bad outcome. It would change your sample sizes. But if the study is all about categorical data, successes versus failures, and by the way, what would you say a success is in this problem? Yeah, I would agree. It would be dying to whichever respective drug. So if we're dealing with successes and failures, and we're recording as a success, the rat has died, that means the sample sizes are right. They're part of the study, and that was just an outcome we were looking into. Let's say that right here, a success. Usually we write that in blue. Maybe let's do the same here. A success is the outcome of the rat dying. So it's a pretty grim study in all honesty, and this would not be one you really want to be working on necessarily, but we're getting through it. Sometimes grim data like this are important. These rats, they gave their lives, so it's our job to analyze these data appropriate and as precisely as we possibly can. So now we know what the successes are, we know what the sample sizes are. That means we know what the statistics are. So 90 dead here means just 90 successes. So X1 is a success for the first group, but I'm forgetting here, we're going with more descriptive subscripts. X sub C is number of successes in the cocaine group. It's kind of nice that they split it in 100 and 100, so that even if they give us percentages, those are just literal counts. We can just say 90 successes here. 36 means XH is 36. And now these lead to the statistics. P hat 1 is just the number of successes, 90, divided by the sample size, to the left 100, and from here, P hat, I guess I'm really used to ones and twos, this is gonna be a struggle, but it's a worthy struggle. Sometimes this really helps us think about the context all the way through, and it gives us a strong conclusion if we try to be descriptive this way. So that was P hat C, and this one is P hat H. Don't hesitate to call out if I forget another one. It seems like that's really easy for me to do. Then take 36, divide by 100. Or if that was a percentage, you could have just said 0.36, but this is the process at least. And we've got our statistics out. Next, we're giving a confidence interval. And looks like this one is a complete analysis, so we'll analyze it in that kind of way. First, we want the practical question on this one. Well, if you cited this, I don't think I'd be terribly opposed because we have all of the context down below what's really going on. We did in the last problem directly cite something out of the problem statement itself to count as a statement phase. So let's go slightly differently. Let's answer this by saying, is cocaine or heroin more deadly to rats in this laboratory setting? That'd probably be what I would go for on this one. Any additions or exclusions that you want to throw in there at the moment? Okay, notice we definitely don't say on average for this problem because this is categorical data. I would say if you left it just like that, that would be okay. For quantitative data, it's a good idea to really mention we're talking about averages. Otherwise, it feels like we're talking about an individual, not the whole population. Now, below, we'll be more specific on what we're doing in the statement phase if we nail down what the parameters themselves actually are. So we go to each one of these statistics indicated and write down the following. Let P take the hat off because now we're talking about the population proportion of successes. Let PC and PH denote the true proportion of deaths in lab rats after, sure, this was in a 30-day time frame. So I'm going to paraphrase it just a little bit and just say unlimited access to the particular drugs that were used. You don't have to mention every bit of it when you write out your parameter. If it feels like it's turning into a long paragraph, it's appropriate to try to find ways to shorten it up. So I'll say proportion of deaths in lab rats after given unlimited access to, now we're going to use that respectively structure like we mentioned before. We should mention cocaine first. We should maintain the parallelism and just literally write in and then say heroin respectively. And if you said for 90 days, no harm either. Really, it's always your judgment call on how much detail you want to put inside there. As long as I see some context here, that's usually what I'm looking for. And whatever the major thrust of the study is, you'll capture here. Just make sure it's included somehow in the statement phase when you write in your parameters. So this one is going to be a confidence interval. Well, I mean, we haven't even discussed the hypothesis test yet. So that's why we're not going to indicate hypotheses. Then the very next thing we're going to do is check conditions. Any questions so far to this stage? Okay, condition checking is pretty much just this table right here, but it helps to also include what we specifically said a success was. Now recall for the large sample confidence interval, we want 10 successes and failures in both samples. Looks like we easily make that. So let's just be specific with what we write down here to indicate that outcome. Let's say first, in the cocaine group, there are a success is dying. And so it looks like over here, 90 successes. Let me put in greater than or equal to 10. Just as a reminder, that's the benchmark that we're trying to fulfill. So there are 90 greater than or equal to 10 successes. And that means with the sample size of 100, there's only 10 failures. We barely made it, actually. It looked like this would have qualified with this total sample size of 200 from both groups, but it only barely made that benchmark. Let's say and 10, which is greater than or equal to 10. Strange thing to say, but that's the benchmark we need to pass. Failures. Only 10 survivors. That's kind of grim again. Now we have to do this again for the heroin group. We'll say, likewise, in the heroin group, there are 36 dead after 90 days, or 36% dead, which means 36 greater than or equal to 10 successes. And that means 64 failures. Definitely meets that benchmark. of greater than or equal to 10. So we need a conclusion here. We met all benchmarks, all successes, all failures in both samples exceeded or was equal to 10, again, just barely. So we are able to say the sample sizes are large enough. And the other thing we know about this problem is they started with 200 laboratory mice. They're all pretty similar. They're all treated very nicely, cages maintained as well as possible. Then they, by randomization, split them into 2 independent groups. We want the mice as similar as possible, same age ranges, same kind of breed, all that, rats rather, all those kinds of things. Because when we introduce them to 2 different groups, we want the outcomes to be all about the actual treatments that they got. So randomly assigning them to the 2 independent groups did give us independent samples and random data all at once. Let's say here just very briefly, since this was and controlled, let's not say controlled, there's actually not a control group here when you think about it. A control group would be another set of 100 rats just on standby, normal conditions, just so we can compare them against. This one has no control group, so that's a bit of a concern on the experimental design. Let's say here, though, since this was an experimental design, with random assignment, to the treatments, treatment groups being the cocaine group and the heroin group, we have 2 simple random samples from independent populations. So the conditions on this particular problem are fully met. However, we might criticize the actual structure of their experimental design. Kind of a weird one when you think about it. Maybe it was a cost decision there, really. We should give an overall conclusion to everything here. So let's just say overall, conditions are met. So we can analyze this data and have some really great confidence on what our conclusion would be. So that's what we're going to do next on part 2, actually doing those computations. Usually it's a big write-up for this kind of stuff now that we're in chapter 20, because it's like checking conditions twice, essentially, one for each one of the independent populations. And because we knew it was an experimental design, we actually had a lot to say about that this time. But any questions or comments, folks, on condition checking this time? Okay, let's get to the fun bit where it's just the mathy part of this, doing the computations. So let me grab a new screenshot, taking what we've already pre-computed, the statistics on the right over there. Or to finish this off, the first thing we should do is maybe just cite the formula we're about to use. It goes p hat c minus p hat h, add or subtract z star, multiply it against standard error, p hat c minus p hat h. So let's just decide on an order of operations for this. Our confidence level was 0.99. That implies a value for z star. And funny thing is, I think a lot of people know the one on 0.95. Anyone happen to memorize the one for 0.99? Occasionally people sometimes do in this class. It's kind of always interesting who has a really amazing working memory like that. Or maybe you're just really fast on the R syntax. That's always a possibility. To compute this one from scratch, you could go to chapter 14 or chapter 19 to see the guidance. This chapter has information too. But it's always the same for z star. Go Q norm. If it was a t star, we would have gone QT for the t distribution. Take 1 minus the confidence we're dealing with, 0.99, divide by 2, and set lower, dot tail, 2 false. So that's our standard operation. If it was a T star, we'd also have to give degrees of freedom. And here's the output down below. Critical number is 2.5758. It doesn't hurt to just share that syntax. Let's see, let's throw it in this way. So that value right there equals the Z star that we just cited. So we've got a couple things out of the way. We've got all the statistics, we've got Z star. Next thing we need to compute is that standard error. So let's do this maybe on the right now. Standard error of P hat C minus P hat H is rather large square root, but we'll just jam it all into the calculator just as normal. It's going to be P hat C times 1 minus P hat C divide by sample size for C cocaine group. Then do it again. P hat H, 1 minus P hat H, divide by NH. Now ready to drop in values and send it to the calculator. So this is square root of, let's actually change these to now proportions. 90 over 100 is now 0.9 times 1 minus 0.9 is going to be the 0.10. Sample size in the cocaine group is right here at 100. Then add, and we do it again. P hat H, that one is a 0.36. So 1 minus 0.36 is going to give us a 0.64. Then divide by 100 again. Now, small comment on this is, you could observe that this formula actually would simplify a lot if the sample sizes were always equal. You could just factor out, hang on, that's not the quite right thought. The parameters would be different. I'm thinking of hypothesis testing. In hypothesis testing, we were able to simplify this formula a little bit further. But at the moment, we're stuck with this particular formula in that form. We just need to get standard error next. Sorry, that was a weird errant comma. I think I'm thinking of the next section of the notes coming up. So now let's throw this all into the calculator, see what we get out. Carefully as we go, this is going to be square root 0.9 times 0.10 divide by 100 plus, this is good to do in a standard calculator, but if you're using RStudio, don't forget you really need that time symbol right there. Then 0.36 times 0.64 divide by 100 again. So that should be our computation. And we have altogether, let's keep 4 significant digits as before, 0.05660. Okay, I think we're just about there, folks. Let me double check my numbers. I have a habit of importing these incorrectly. Any questions at all to this stage? Okay, with our values out, we're now ready to return to the formula from here and just fill it all in. I think we can get rid of this white noise here as well and just focus on the elements we need. So take this. In our next step, this is going to turn into, I take that back. I need that actually. Let me bring this back for just a moment. Okay, the next step with the data down below cited nicely, we get first P hat for the cocaine group, that's over here at a 0.9, minus P hat for the heroin group, and that's down here as a 0.36. Then add and subtract the critical number that we found, 2.5758, which is multiplied against standard error at value 0.05660. So this is the entire confidence interval. I think we're officially now actually done with that. We'll jam this part into the calculator, but don't forget what we're actually estimating here is P1 minus P2. We're going to find bounds that constrict both of those parameters, or the difference in those two parameters. Let's also get this ready. We'll need it for the conclusion. So now at this point, back to the calculator, we're focusing just on this portion right here. So parentheses are kind of helpful sometimes just to organize what's going in. 0.90 minus 0.36. Starting with the minus for the lower bound, 2.5758 times 0.05560 gives us this lower bound here. So we have something close to about 40%. Let's take a 0.3968. Then one more run. Let's flip this sign right here to positive. This is where the parentheses help me a lot because I think I mentioned this before, have a habit of flipping that negative to positive. Will not work whatsoever. So this comes out as a 0.6832 next. But don't forget, those are also percentages. If you like, in your interpretation, you could cite them as percentages, or you could just keep them as proportions. Lots of stylistic choices on how you would want to write after conclusion. But we do have to mention the level of confidence, and we do have to say what P1, P2 really are. Well, any questions at the moment so far? Yeah. Oh, thanks for mentioning that. Yeah, forgot about our relationship between the two variables. P1 is really PC. Thanks for spotting that. True proportion for the death rate in the cocaine group. Kind of confusingly, when you say death rate, the rate already is referring to a proportion, so it feels redundant, kind of interesting wording. And then pH. Other questions so far? Okay, let's give our conclusion. Confidence was at 99%. Maybe even before we give that conclusion, a lot of people are possibly okay giving conclusion right here, but I wouldn't necessarily want to say the difference in the death rate between the cocaine group and the heroin group is from 39.68% to 68.32%. It sounds like a word salad even to me as I'm saying it out. There's just a lot you're expecting the reader to do as a mental backflip. What you could do is, let's isolate one, the cocaine group, just because we add pH to both sides. It's an easy way to isolate it. If we did that, we would get 0.3968 plus pH less PC, which is now less 0.6832 plus pH. If you do it this way, you can now say the death rate in the cocaine group is 0.3968% higher than the death rate in the heroin group, to this much higher than the death rate in the heroin group. So it can read a little bit differently. But even this is a stylistic choice. Pick which way that seems to make the most sense to you when you write down the conclusion. If the conclusion makes the most sense to you, then that's probably the better one to give, is my advice on this. I'm going to go on the bottom line here by the red line and say, now, with 99% confidence, I want to refer to this parameter here. It's the true proportion of deaths in labs after unlimited access to cocaine. So I'll say that part. The true proportion of deaths in lab rats given, let's just say, unlimited cocaine to shorten that up a bit. So we just mentioned that parameter. And now we can say is from this value to this value. I'll keep it as a proportion since I mentioned proportion once already right here. So I'll say is from 0.3968 to 0.6832 higher than because the signs are positive. And then we mentioned pH. We already have part of the context here, so we don't have to duplicate the entire thing. We're still talking about lab rats, and we're still talking about proportional deaths. The thing we're switching is unlimited access to heroin now. So we'll just say higher than rats given unlimited access to heroin. Then finally, that's our conclusion. Any questions or comments, folks? Finally getting to that last step. Okay, we have to ask ourselves now, because this was a complete analysis, did we answer the question in the statement phase? The statement for our practical question was, is cocaine or heroin more deadly to rats in this laboratory setting? But with that conclusion we gave, certainly, we just said cocaine has a death rate that's almost 40% higher to almost 70% higher than the death rate in the heroin group. But it doesn't hurt to just restate this. This shows cocaine is clearly more dangerous in this context. Again, these kind of studies, it's not just about the rats. It's not as if we want to know everything about rat society and how drugs affect them. This is more, we want to turn this over and start analyzing human behavior now. So this is one of the first steps, see what happens in something that's easy to understand. The ethics are a little bit different. We're not giving humans unlimited access to these drugs. That would never pass an ethics board, for example. But it gets us closer to making strong statements about human psychology or human behavior when we do these kind of weird experiments. I forget how old the study was. I think it's a pretty old one as well. But that's now the methods for doing a confidence interval if you have two population proportions. You'll notice the methods are really, really similar to what we did in chapter 19. Major change is really just the standard error and the fact that you're subtracting things here and down here when you get your final estimate. So we're going to turn this over to take a quick look at what's going on with hypothesis testing. But I don't want to necessarily start the very next question, because I don't think we would be getting too far into it. We'd be breaking this one in half. So what's next one? It looks like it's all about biology, where the last one seemed to be more about human psychology, human behavior. We're going to look into a so-called Trivers-Willard hypothesis, kind of an interesting one in biology, to see if we can get some statistical significance here. But this one is going to be a hypothesis test, so let's see just how to analyze that situation. When you do a confidence interval with categorical data, it's not too weird, but the moment you step into the realm of hypothesis testing, huge changes will occur. So example 3 is just a kind of a warm-up phase before we go into the full method of what is the hypothesis test. Here's what the setup would be, though. We have to have two independent, simple random samples. Sample sizes are indicated as N1, N2. Populations have proportion of successes, true population proportion of successes, P1 and P2. Our null hypothesis is that P1 is P2. Let's hold that thought for just a moment. This is so strong in parallelism to this chapter over here. It doesn't hurt to take a look into how would it go back in this situation. Once I get to the right spot. Sorry for the random scrolling. Oh, not quite finding it. I think my thought was rather what we're doing in chapter 19. Apologies for the random mental breaks here. In chapter 19, when we turn this over to a hypothesis test, here's the weird stuff that started to occur. There we go, finally. So when we were dealing with the hypothesis test way back, not too far back in chapter 19, we automatically assumed that the null hypothesis was true. But then from right here, that gave us humongous amounts of information. Assuming the null hypothesis is true, gave you the value for the parameter. We're directly assuming P is P naught for 0.35. So we just went up here, directly filled it all in. Something like that happens over here as well. The first step that we take in analyzing these hypotheses, P1 equals P2, P1 is not equal to P2 as a two-tailed test, is assume H naught is literally true. We're going to assume that's our reality. The null hypothesis is the truth about the populations. This has some really interesting ramifications, though. If the null hypothesis is true this time, a little bit different than in chapter 19. We gave it a specific value. We knew that value. We're directly testing 0.35. But here the hypothesis test, much like in chapter 18, is that the parameters are the same. We don't have further information on what is the common value if they're the same. We'll just write it out this way. Let P1, which is equal to P2, now be equal to P naught, the common value that they're both equal to. So assuming H naught is literally true, as assumed P1 equals P2, and so now that's the common value, P naught. We need to know the sampling distribution of P hat 1 minus P hat 2 under that reality. So let's cite our central limit theorem from above. First, any questions at the moment with this statement so far? Okay, let's say here, the sampling distribution of P hat 1 minus P hat 2 is P hat 1 minus P hat 2 distributed approximately normally with parameter P1 minus P2 for the center, and for the spread, it's going to be square root of parameter P1 times 1 minus P1 divide by N1, then plus, let me back off a bit there we go, P2 times 1 minus P2 divide by N2. Each time I write these square roots, I try to make them long enough, but it never seems to work out in statistics. This stuff gets pretty long-winded, it looks like. So that's the sampling distribution of P hat 1 minus P hat 2. Let's put a comma here and say, but when H naught is true, P1 minus P2, well, if they're both equal to P naught, P1 minus P2 is 0 now. And so that's actually before the end, so let's back off of just a bit. We can also make a statement about this part inside the square root. And P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2 becomes, everything is P naught now. So this will be P naught, 1 minus P naught over N1 coming from right over here. Then P2 also equals P naught through a null hypothesis. So plus P naught, 1 minus P naught over N2. Here's where I had that random errant thought about how you could simplify the formula. If the null hypothesis is true, it really does simplify, because now we have a greatest common factor across these numerators. We can now just factor out P naught, 1 minus P naught, leaving behind 1 over N1 plus 1 over N2. So really interesting algebra through the statement here, giving us a third variable equating both parameters, means center is 0, And this complicated structure, we're going to put a square root on it, turns into this slight simplification. Here's our overall conclusion. Therefore, p hat 1 minus p hat 2 is approximately distributed normally with the center exactly at 0 and the spread, the standard deviation being square root of all this stuff right here, p naught times 1 minus p naught times 1 over n1 plus 1 over n2. So our central limit theorem takes a whole different form. One of the reasons we do these kind of problems is just give a little explanation. Why do the formulas change so much, even within the same chapter? It's all because of that assumption being a really radical one with categorical data. Huge ramifications occur next. Next thing we can do is find the standard error, p hat 1 minus p hat 2. But this gets even crazier on the next step. So let's be really mindful of how the next part goes as well. So if we're going to do the standard error, p hat 1 minus p hat 2, it's a whole new standard error, absolutely. Maybe let's make that our first warning on this. Not the same standard error used in confidence intervals. And we mean the confidence intervals in this chapter itself. Standard error changes a lot. And here's the logic behind why it does. Ordinarily, if we're going to grab a standard error, what we do is we take something over here and build an estimate, right? But what in the world is the estimate this time? It's going to be based on estimating p naught. So that's going to be our first job here. And estimate for p naught is, let's pause right here in the moment and remind ourselves, what exactly are we doing? We're testing that null hypothesis that the parameters are the same against a two-tailed test. But if we do that, we assume, first and foremost, the null hypothesis is true in hypothesis testing every single time, no matter how weird it gets. But if you assume the null hypothesis is true, this line is saying your populations were the same. They behave the same. The parameter is the same. And therefore, if you're going to estimate this parameter p naught, just go back to your sample data. P hat 1 is estimating the same parameter as p hat 2. We're essentially saying it came from the same population. They're not different. If that's the case, we'll leverage both statistics at the same exact time to estimate p naught, the common value. So an estimate for p naught is the pooled sample proportions, proportion, singular, of successes defined by, I hate this part, it's defined by p hat. That is the notation our author gives. We just have to know if this p hat comes up and we're dealing with two dependent populations, absolutely not the p hat of the prior chapter, chapter 19. This one's different. It goes x1 plus x2. Those are the successes in the first sample and the second sample. Both samples are estimating the same thing, so we just add those successes together, and we add the sample sizes n1 plus n2 together. So we first estimate p naught by this p hat. Then, let me see if I have enough space down here. The standard error is, let's try it out as SE. It is the standard error for p hat 1 minus p hat 2. But if we wrote that in, I feel like that could be highly confusing. But we're kind of in a weird spot. If we put in standard error p hat, That's equally confusing. That sounds like chapter 19. So I think the best approach is just write in standard error, p hat 1 minus p hat 2. We have to know this is only purely in the context hypothesis testing. It's going to become square root of p hat right here estimates p naught, the pooled proportion of successes. So p hat would go here. 1 minus p hat goes here. Then it's 1 over n1 plus 1 over n2. So let's see, can we give a good way to indicate this? Some special color. I'm running out of colors for color coding, but let's go this route. Estimate for P naught is the pooled sample proportion of successes defined by this P hat. And so that's the P hat that goes here and here. Honestly, I think that makes it just too busy visually if we put too much stuff on there. But that's our new P hat value. Any questions at all, folks, getting to that in there? So we have a new standard error. That means the test statistic has to reflect that. But this is the easier part of the development. We can now say the test statistic is still Z. We call it Z because p-values are from the normal distribution. What Z is going to do is measure the distance between the data, p hat 1 and p hat 2. If they're really coming from the same population, if they're really estimating the same parameter, p naught, they should be close to each other, right? So we want to know how far away is p hat 1 and p hat 2 in terms of standard deviations. By standard deviations, we mean this thing. And I think it's easier to just throw it in as a big overall formula so we don't get as sidetracked by the standard error. So let me just throw it in officially this way. P hat 1 minus p hat 1 over n1 plus 1 over n2. So that's our new test statistic. It measures the approximate standard deviations. P hat 1 is going to be away from p hat 2 under the assumption the null hypothesis is really true. So if we make all those assumptions, and this comes out to like, say, 12 standard deviations or even 3 standard deviations, we'll say that's highly unusual. And the only way we got here was because we made that assumption. Maybe it's false, and we'll use a significance level alpha to guide us on that. So if the standard deviations are too high, the p-value will be very low, and we'll reject that reality outright, even though we were running with it for quite a while. We'll assume this is the more likely reality about the population. Parameters are different, and the samples really came from different samples. So that's the logic of hypothesis testing with 2 independent populations. It is really pretty weird. So when you go to do these kind of problems, be very mindful of the pooled sample proportion of successes. Out of nowhere, this is a pretty weird statistic. Maybe the weirdest one we're going to encounter all semester. It's pulling samples because it's based off the null hypothesis being true. Once we have that, our standard error, it's like I called it a p hat on these notes, becomes this result right here. But everything else is just exactly the same when it comes to the p-values. So what we'll do is, instead of launching into this problem over the course of about 6 minutes, we'll come back and finalize this one here on our next Tuesday, and then take a look into some chi-squared procedures. But any last questions or comments, folks, developing down to here for the hypothesis test? Okay, definitely strange logic. The strangest thing about all this logic is hypothesis testing is really just weird. Even when you're studying in a course like this one, it's actually not a bad idea to go all the way back to chapter 14, where the author was introducing hypothesis testing for the very first time. When you read that reading first, it's really hard for your brain to make heads or tails of what the author is saying. But now that you've been exposed to this much hypothesis testing, the reading in chapter 14 is like 10 times more impactful. You'll know what the author's talking about at every little detail. So going back to rereading prior sections is really, really helpful now at this stage of the course. But looks like I pretty much ran literally out of things to say, so we'll call it a day here. If you have any questions or comments over the weekend, I'll be happy to help out. And again, I'll be posting the exam 3 review materials and the formula sheet starting on Friday. I'll be working on it, finalizing on Sunday. Your homework might come a little bit late sometime on Sunday, but I'll definitely get it in. Well, any last questions at all, folks, before we call it a night officially? Okay, have a great evening, folks. We'll reconvene on week 13, nearly there.